This is lesson 6.2, where we will look at systems of three linear equations. So in this example that I have written below, we see three linear equations. And notice they also have three variables. Okay, so I'll number these equation 1, equation 2, and equation 3. Okay, so let's just solve this example to demonstrate how to do this. The idea is to concentrate on two equations, and we will eliminate a variable out of here. So if we look at these equations, equation 1 and 2, we notice we can eliminate the terms with y in it pretty easily. If we just add equation 1 plus equation 2, then the terms with y will cancel out. So notice we have 5x plus 3y plus z equals -30. Right, that was equation 1. We also have x minus 3y plus 2z equals -6. That was equation 2. So if we add these two equations, we get 6x, and then these terms with y's cancel out. We get 3z, and we get -36. Okay, so what do we do with this equation? Well, this is just one equation with two variables. So it's not enough to solve for the two variables. Remember, if we have two unknowns, we need at least two equations. Okay, so we're going to have to do this same thing again using the forgotten equation. We haven't discussed equation 3 yet. So we're going to have to eliminate the y again, but this time we will incorporate the equation we did not incorporate last time. Right, so we need to pick this equation and one of these two to eliminate the y term in equation 3. And then we will have a system of two equations, two unknowns. So let me rewrite equation 3. It's 14x minus 2y plus 3z equals -54. That was equation 3. And then we have the choice. Do we want to use this or this to eliminate this y term? Well, I guess I'll pick equation 1. They both are not very good, but I could just pick equation 1. Okay, so this is equation 1. Now, if we just added these equations, the y terms will not cancel out. So what I'm going to have to do here is multiply a 3 to both sides of this equation, and let's multiply a 2 to both sides of this equation here. Now when we add the two equations together, the terms with y in it should cancel out. Okay. But first let's just crunch these numbers. So we have 14 times 3, let's see, 14, 28, 42, so we have 42x. So what I'm doing here, I'm just multiplying through 42x minus 6y plus 9z, and then on the right hand side we will have -54 times 3 -162. Okay, now let's multiply the bottom equation out. We have 10x plus 6y plus 2z is -60. Okay, now we can add these equations together, and the terms with y will cancel out. We have 52x plus 11z equals negative 162 minus 60, so negative 222. Okay, let me circle this in purple. So now if we look at these two equations circled in purple, we have two equations and two unknowns. So we can solve this purple system now using the methods we learned in 6.1. So let me rewrite the system we just came up with. We have 6x plus 3z equals negative 36. We have 52x plus 11z equals negative 222. Okay, we can solve this using the methods in section 6.1. So remember, we learned substitution and elimination. Neither one is going to be very easy in this example. These are not that great of numbers to work with, but let's just use substitution. So we could rewrite the top equation. Let's rewrite this top equation as 6x equals negative 36 minus 3z, and divide everything by 6. We have x equals negative 6 minus 1/2 z. Okay, and then we plug in to the bottom equation. So the bottom equation is 52x, but x can be written as minus 6 minus 1/2 z. And we have plus 11z. And then this equals negative 222. Okay, so 52 times negative 6 will be negative 312. And then 52 divided by 2. We have 26z. And we add the 11z, and equals negative 222. Okay. So now we could just solve for z. Okay, so what do we have? We can combine the like terms. We have negative 15z. And if we add the 312 to the other side, what do we have? It's 312 minus 222, 90, so we have negative 15z equals 90. Z is 90 over negative 15. 90, so z equals negative 6. So we solved for one variable. Now we know z is negative 6, right? So let's go back to the original system. We know z is negative 6, but we still need to know x and y. Well, we could find x by looking at this simpler system that we came up with. So we found that z is negative 6. So let's just go back to the simpler system that we came up with and solve for x now by plugging in the z. We plug in the z, and now we can solve for x in this 2 by 2 system. Right, so see this equation that we came up with here? Let's just plug that z equals negative 6 result in. plug into the easier two-equation system. Alright, we could just plug into one of the equations here, say the top one. We have 6, what was the equation? 6x plus 3z equals negative 36. So 6x plus 3, 6. Okay, so now it's pretty easy to solve for x. You have 6x minus 18, 36. So we just add the 36 to the other side, or sorry, we add the 18 to the other side, and we get 6x equals negative 18. Divide the 6 over and we get x is negative 3. Okay, so now we know 2 of the variables. So we go back to the original system. We know the z, we know the x. We still don't know what y is. But since we know z and we know x, we could just plug into one of these equations and then solve for the y. Alright, so now that we know 2 out of 3 of the variables, we just plug in to an equation of the original system. Okay, so let's do that. One of the equations was x minus 3y plus 2z equals negative 6. So let's plug into x minus 2y. Or sorry, what was it? X minus 3y plus 2z equals negative 6. So we can plug in the x equals negative 3, the z equals negative 6. Okay, so we get negative 3 minus 3y minus 12 equals negative 6. Okay, so we could add the 12 to the other side and add the 3 to the other side. So negative y equals 9. Y equals 9 divided by negative 3. So y equals negative 3. Okay, so to summarize, x is negative 3, y is negative 3, z is negative 6. So the solution is x was negative 3, y was negative 3, z was negative 6. There is the solution. Okay, so to summarize, we started with a system of 3 equations, 3 variables. First, we picked 2 of the equations and reduced it to a 2-variable equation. But then we needed one more 2-variable equation, so we picked another 2 of the equations, this time picking the forgotten equation, and found another 2-variable equation. And then once we had this 2-variable system, we solved using the 6.1 methods, so we were able to solve for those 2 variables. Once you have those 2 variables, you just simply plug into an original equation and get the 3rd variable. And that is how we solve the 3x3 systems. Now, similar to the systems in 6.1, we can have one unique solution, or we could have no solution, or we could have infinitely many solutions. So the problem we just saw was an example of a unique solution. Right? We got a value for x, a value for y, a value for z. Now we can look at an example where there is no solution. So this is a no solution example. So let's consider the system 3x minus 5y minus 4z equals 6, 9x minus 15y minus 12z equals negative 10, 2x minus 3y minus 5z equals 4. Okay. Okay, so let's see what happens when we try to solve this system. Let's just try using the same method as above. Look at these two equations, for example. So I'll call that equation 1, that equation 2. If we rewrite those, say we have equation 1, 3x minus 5y minus 4z equals 6. Now let's write equation 2, 9x minus 15y minus 12z equals negative 10. Okay, well, let's try to eliminate a variable. It doesn't matter which variable we eliminate. Say we want to eliminate the x. Well, then we will multiply the top equation by negative 3. That way we'll have a negative 9x on the top equation and a positive 9x on the bottom equation. Right, so after doing that, we come up with the system negative 9x plus 15y plus 12z equals negative 18, right? When we multiply these numbers out, this is what we get. In our bottom equation, we didn't do anything to it. It's still just 9x minus 15y minus 12z equals negative 10. Okay, so let's add these two equations together now to eliminate the x. Well, it just so happens that the y terms cancel out as well, and the z terms cancel out. So on the left-hand side, we get 0, right? Everything canceled out, so the left-hand side we get 0. But on the right-hand side, we get negative 28, right? So if we assume there's a solution to this system and try to solve it, we end up with this contradiction that 0 equals negative 28. Right? Clearly a contradiction. And therefore, there is no solution. So there's no solution. So if we assume there is a solution, then it would follow that 0 equals negative 28. And that is a contradiction, so therefore there is no solution. Okay. Now let's look at the other case, the third case, where there's infinitely many solutions. Okay, so here let's consider x minus 3y minus z equals 3 minus x plus 8y minus 4z equals negative 8, 2x minus 15y plus 7z equals 15. So here is the system. And again, we solve it in the same way as usual, we will just pick two equations and try to eliminate one of the variables. So this is the easiest two to pick, because if we add these two equations, then the x's get eliminated, and that's good. So if I rewrite those two equations really quick, we have the following. Okay, so we simply add these two equations and the x's are eliminated. And we have 5y minus 5z equals negative 5. Okay, so there's one of our two variable equations. And now we need to come up with another two variable equation using this forgotten guy, the equation that was left out. Okay, so now the left out equation was 2x minus 15y plus 7z. 7z equals 15. And then say I want to use equation 2. I could have used equation 1, but it does not matter which other equation you pick. Okay, so that's equation 3 and equation 2. Now if we just add or subtract them, nothing gets eliminated yet, and we want to eliminate the x. So I'm going to multiply a 2 to both sides of this equation. That way we can eliminate the x pretty easily. Okay, and then the system reduces to, well, let me just copy down the first equation. We have 2x minus 15y plus 7z equals 15. And the bottom equation comes negative 2x plus 16y minus 8z equals negative 16. Let us add these equations. The x's are eliminated. We get y minus z equals negative 1. Okay. Now you could try to solve this equation using the methods in 6.1, and you would end up with the infinitely many solution case. Hopefully that's obvious, because if we just multiply this equation by 5, then we get this equation. So these two equations are the same thing. It's just this equation you multiplied both sides by 5. Right, so this equation that I have circled in purple, or this system in purple, is 5y minus 5z equals negative 5. The other equation is 1y minus 1z equals negative 5. Well, this is clearly the infinitely many solution case that we learned about in section 6.1, right? Because the top equation and the bottom equation are the same thing. It doesn't matter that you multiplied both sides by 5 on the top, it's still the same equation as the bottom one. At least it's the equivalent equation. So since there is infinitely many solutions, what we do here is we just solve for the z. So z, negative z would be negative 1 minus y. Z would be 1 plus y. Hold on, let me see if I might have made a mistake here. Let me look. So we could leave z just as that. Let me make sure I didn't make a mistake here. X 3 Okay, sorry, I think it's correct. Anyways, so we could leave z as 1 plus y, or we could solve for y and leave y as -1 plus z. So whatever way you want to do it, you just solve for one of those variables. So typically what we do is we will let z be any number. Since there's infinitely many solutions here, we could plug in any z we want. And then the solution for y is given by, in terms of z, here's y equals -1 plus z. So since there's infinitely many solutions, how we handle this is we just say, well, let z be any one of those infinitely many numbers, and then y will depend on z. Right? And then, so we kind of can solve for x now. Just think of these as fixed numbers now, even though they still have variables in them. We did the best we possibly can in solving for them. So we just plug these back in, and we will get an x in terms of z now. So now we find an x in terms of z. So our solution for x will also have some z's in it, right? So we look at the original equation. We could just plug into any one of these original equations. So let's do x minus 3y minus z equals 3. X minus 3y, what was it? Minus z equals 3. Right, that was an original equation. Well, we could plug in the results we found. Right, for this y, we could plug in this result here, the -1 plus z. And then z we just leave alone, since we couldn't solve for all the variables. We just let z be any number. Okay, so now we have x plus 3 minus 3z minus z equals 3. Okay, minus both sides by 3 goes away. X minus 4z equals 0. X equals 4z. Okay, so we got that. This for our solution. We could plug in 4z for the x value, -1 plus z for the y value, and any z. So this is how we handle the infinitely many solutions. We just fix one of the variables, so the x value and the y value will depend on this free variable here, the z. So that's how we handle the infinitely many solutions. Even though there is infinitely many, we just found a formula for any of those. So you plug in any z value, and then we get a solution. So we found the general form of the infinitely many solutions, or a general formula that describes all infinity solutions of this system. Okay, and that covers all the cases in this lesson. So to summarize, we started with a problem where there was the unique solution, and we just got a number for x, a number for y, and a number for z. Then we looked at an example where we came up with a contradiction and had to conclude there was no solution. And then in this problem, we couldn't exactly solve for all the variables, so we just did the best we could and fixed z, and then got the term, the x term and the y term, to have z's in it. That's the infinite solution case. And we will end today's lesson with that. Thank you.